Okay, everyone, I have 7:31.5, so we'll call the meeting to order, and we will start off like I did last month. I promise this joke will be a little bit better than the last one. Sherlock Holmes and Dr. Watson were going camping. They pitched their tent under the stars and went to sleep. Sometime in the middle of the night, Holmes woke Watson up and said, "Watson, look up at the stars and tell me what you see." Watson replied, "I see millions and millions of stars," Holmes said. And Holmes said, "And what do you deduce from that?" Watson replied, "Well, if there are millions of stars, and if even a few of those have planets, quite likely there are some planets like Earth out there. And if there are a few planets like Earth out there, there might also be life out there." Holmes said, "Watson, you idiot, it means someone stole our tent." Yeah, that was better than last month. Great. So I'm hoping to get better as we go on over the course of the year. Anyway, meeting from February 10th. The meetings are available on the members area on our website. Has anybody read? Hope somebody has read them, because if there's any errors or omission, can you please let me know? Yeah. Seeing nobody urgently saying we had some problem, we'll have someone make a motion to accept the February 10th meeting that's posted on the members area on the OneDrive. Tom Owen made that motion. Do we have a seconder? Okay, did you get it? Did you get his name? Okay. Thank you. Any questions? All in favor, say aye. Okay. Anyone opposed? Seeing none, motion is passed. Okay, number 2, we have a special presentation to make today. So I want to have Tom Owen and Jeff Robertson come up to the stage, please.
What's this for? You'll see. Oh.
Okay, there's something called, and I'm going to use the Inuit pronunciation that we only discovered earlier today, called the Kalak Award. It's an Inuit word meaning the entire sky, the celestial sphere, and all that it contains, the sun, the moon, and the stars. This award at National was established in 2011, and the awards are given one by each of the sponsoring organizations with the common purpose and evaluation criteria. This award is intended to recognize individual Canadian residents or teams of residents who have made an outstanding contribution during a particular time period, either to the public understanding and appreciation of astronomy in Canada. Okay. Anyhow, so without further ado, we would like to say that this year's winner was Jeff Robertson.
Okay. I've never heard of this.
It's a national award.
I've never heard of this.
Okay. Get the right piece of paper here. There we go.
Is there any money involved?
That's some kind of a plaque.
Oh, okay.
I heard it might be a couple mil, but you know.
All right.
Okay, so this, we had to have 2 people from our organization here in Edmonton to nominate Jeff, and they were submitted by Jay and Tom. And so basically, here's what was written by these 2 gentlemen for Jeff. Jeff has performed in many roles throughout his RASC Edmonton Center tenure, including Vice President, President, Observing Committee Chair, and Public Education Director, to name a few. His most recognizable contribution has been creating and conducting the What's Up Over Edmonton program. Jeff spent an enormous amount of time putting together an outstanding 1-hour educational session for members and the general public. All sessions eventually being posted on the RASC Edmonton Center YouTube channel, each with hundreds of views. The amount of time and effort it took for the program together is nothing short of remarkable. After several years of providing this wonderful service, Jeff has decided to hang it up after December 4th, 2024. We think the KELAC Award is an excellent award recognizing Jeff's contribution to the RASC as well as astronomy public education. Another round of applause for Jeff.
Thanks.
Thank you, sir.
Certificates in the mail.
Yeah, the check is in the mail. But yeah, Jeff will be receiving an award, a plaque commemorating it. But I think all of us here really enjoyed his What's Up Over Edmonton, the contribution over the year. I know I looked at him on a number of occasions, and they never failed to entertain, to say the least. Thank you again, Jeff.
Thanks.
Oh, by the way, when you do get the plaque, we'll bring it in and we'll get another presentation with pictures and the whole work.
Oh,
Thank you. Thanks, Tom. Okay, treasurer's report. Jeff, unfortunately, cannot make it again today. So basically, not much has changed since last month. We ended the month with $74,690 and change. We started at $75,330. Credits were primarily from membership dues and public donations. Expenses for the month were attributed to membership pins, handbook, and our membership fee program. Casino account started at $121,924. We ended the month at $121,653. Expenses were attributed to reimbursing speaker expenses and display pictures. The Bob Drew Telescope Fund, it was a donation from Bob for $25,000 in support of developing the UDT. Current balance is $2,516.27, basically unchanged from January 2025. So if anybody have any questions with respect to that condensed report, hopefully Jeff will be back next month, and if there's any details that you want to talk to him about, that'd be a good time to do it. Okay. Guest speaker tonight is Rodrigo Fernández from the University of Alberta, and I'll invite Sharon up to introduce him.
Okay, hello everybody. Gives me great pleasure to introduce Rodrigo Fernández. And this is going to be a little longer too. Rodrigo has been in the University of Alberta since 2016.
You're still doing
Close to his tenure anniversary.
It's a share now.
He's an expert in computational astrophysics. And his main area of interest is basically evolving things to make them explode. So I'm hoping that we will be, this will be very exciting. He's originally from Chile, where he did his PhD, and then he came to Canada at the University of Toronto for his PhD. And he's also been a postdoc in I think this is all working now.
yeah, it should be. And then
So I think say fantastic.
thank you.
So, yeah. Okay, thank you, Sharon, for the introduction, and thank you all for the invitation here. It's a very nice planetarium. It's the first time we do a presentation with this 60 coverage, my slides. So, as Sharon said, I'm a theoretical astrophysicist. I study stellar explosions, so supernova and mergers, and one of the areas I'm interested in is how those explosions contribute to producing the elements that are necessary for life and for everything else that's for us. So the two images that I chose for my first slide.
On the image on the left, you see a planetary nebula, which is the end state of life of a star like the sun. Okay. the outer layers of the star are expelled, and at the center you have a white dwarf. And for a brief period in the life of the star, this gas is ionized by the light of the white dwarf, and then it glows. These are recombination lines, okay? And in red you see, okay, it's visible here. You see nitrogen, and in green we have hydrogen, and in blue we have oxygen. So this shows you that elements are being expelled to the interstellar medium, and then they mix up. And similarly, on the right, we see the Crab supernova remnant. So this supernova was observed in the year 1054, if I'm correct, and 1,000 years essentially almost have passed. And again, we see in high energy, we see a neutron star, of course, inside, but also you see various elements. Both of these images, by the way, were taken with the Hubble Space Telescope. You see various elements that indicate oxygen and I think ionized sulfur. This is the blue one. You see the elements being mixed up into the interstellar medium, right? And these elements are those needed for life: carbon, oxygen for water, right? And when we look at the history of how these elements were made, we see that stars and stellar explosions are involved in the creation of these elements. Okay, so most of you, I'm sure, have seen the periodic table of elements, in which elements are organized by atomic number, and then there's a periodic set of properties related to their chemical properties that were, first found and then help to organize them. But then what you might not have seen is where they come from in the universe. Okay, in astrophysics, we have the branch of astrophysics that looks into this is called nuclear astrophysics. And the different colors here correspond to different sites in the universe where we by now know these elements are formed. Okay, the different colors correspond to different sites. And I'm going to be going through the sites in turn where these elements form, and so that we can have a global picture of where this comes from. Okay, not going to go into any detail about every single site, but just to give you a broad overview. Okay, so the plan of the talk is first to talk about the origin of elements and how we put this picture together, and then go through the different sites, and then tell you about a few of the open questions in nuclear astrophysics that connect to nuclear physics research, but also astronomy. Okay, so the theory of the origin of elements was really organized and put together in the 1950s by Burbidge, Fowler, and Hoyle, and based on the cosmic abundance curve. So what are the relative abundance of different elements that they get from solar observations, from meteoritic abundances, and other things, try to infer based on the nuclear physics where these things could have happened, right? And they, at the time, already realized that there had to be some production in the early universe, some production in stars during the quiescent phases, and some production during explosive phases. Okay. In particular, this curve is very illustrative. You see on the y-axis the log of the relative abundance with silicon at 10 to the 6th. This is silicon, right? And on the, let me just put this to the side here. I cannot get it out of the way, unfortunately. No. Okay, let me take this out of the way. No. Okay.
The minus, the negative.
Where's the minus?
Is this talking or just move it out?
No, it doesn't move. Yeah, whatever. So on the x-axis, you see the atomic number, or the atomic weight, sorry, the mass number A, right? And so it goes from hydrogen, then helium, then elements like oxygen and neon, magnesium, etc. And then there's an exponential decrease, right? This is a log on the y-axis and linear on the x-axis. So it's exponential decrease from hydrogen all the way down. Then a big bump at around 50, which is iron, of course, and iron-related groups. We call that the iron group. And then the slope of the curve flattens out at very high mass number, okay, 100, 200. Right? And then you have this double peak structure, and this N is the neutron number, right? So each nucleus, of course, is characterized by the number of neutrons and the number of protons. So N is the number of neutrons, and those are called magic numbers, nuclear magic numbers, at which nuclei, later on, we have learned, have particular stable configurations, okay? So these are magic neutron numbers that correspond, of course, to the R and the S process, as I'll describe in a moment, okay? And then you have lithium, beryllium, and boron at much lower abundances than the rest of the elements. And then they realize, okay, hydrogen and helium are the most abundant. And from the history of cosmology, we know that they should be coming from the Big Bang, okay? They are the most abundant by far. And very roughly, most of you know, Edwin Hubble observed in the early 1920s that galaxies were moving far away from us, and the farther away the galaxy is, the faster it moves, and that implies that the universe as a whole is expanding, so the expansion of the universe. And then if you turn the time backward, it means that the universe was all concentrated into a single point in the distant past. Okay, and that was conceptually called the Big Bang, right? The beginning of the universe as everything in a single point, as a, if you want, a giant explosion. Okay, and if when physicists started working out the physical conditions in that explosion, you can think of the whole universe as a dense gas that is very hot at early times, and then it cools down and becomes less dense, okay? And yeah, this covers my key equation here, but let me just see if I can just move this out of the way. Okay, almost there. No, doesn't respond. Maybe I can hide this. Okay, those.
I'll try to get that away from you.
Hide loading controls. No, it just doesn't respond. Oh, thank you. Okay. Thank you. Yeah, thank you. All right, so the equation all of you know, E equals mc squared, is really the key here, because at very early times, the temperature of the universe was very high, right? And if you think of the temperature as a measure of the energy per particle, if the temperature is high enough, such that the energy associated to that temperature is higher than the rest mass of different particles, you can create pairs of particles and antiparticles, okay? And that happened very early on in the universe. There were all kinds of particles and antiparticles, and eventually you had free quarks. I'm talking about 10 to the minus 6 seconds in the age of the universe, and those free quarks then combine into neutrons and protons. And then at some point, long story, there was an imbalance between the protons and the neutrons. There were more protons than neutrons by a ratio of 7 to 1. And the reason is subtle. It has to do with the fact that the mass of the neutron is slightly higher than the mass of the proton. So it is energetically more favorable to have more protons than neutrons, because the reaction that goes from proton to neutron costs energy. Whereas we're going from neutron to proton, as you know, the neutron decays into a proton and gives you energy, is energetically favorable, right? So at the point at which fusion reactions could become possible, that was the ratio of neutrons to protons. And the reason fusion reactions were possible, it was very hot, but it was possible because there were also many gamma rays around, a lot of photons. And those gamma rays could break up any nucleus that could form, like helium or any heavy nuclei. But there was a transition in which the universe was cooling and expanding, where the ratio of protons to neutrons was 7 to 1. Gamma ray bombardment was not so effective, and helium could form. And then at about 5 minutes, the density became low enough that normal reactions could occur, but then helium didn't manage to go to the next step, which is to make carbon. Right? All reactions were essentially frozen at that point. And we were left to a ratio of 75% hydrogen and 25% helium and a little bit of lithium. Okay, that was Big Bang nucleosynthesis, as we call it. Okay, and these are the red squares here. Okay, this helium here is made in the little corner here. You see that some of it has other colors. The sun is producing helium, right? So that little bit of helium comes from stars like the sun. Okay, the next site is Di-Loma stars. These are the planetary nebula that I showed you at the beginning. The sun, of course, is fusing hydrogen at the center. That is what powers the solar energy, of course, right? Hydrogen goes into helium. And of course, there are many more stars out there than the sun, as you know. And if they're burning hydrogen at their centers, we say that they are in the main sequence, okay, of the HR diagram. The HR diagram is a diagram that astronomers use to put stars, right, to classify them. And so on the x-axis, we have the temperature from cold on the right to hot on the left. And on the y-axis is the luminosity. 1 is the solar luminosity. We go up to 10 to the 6 solar luminosities, 10 to the -5 and -4 solar luminosities. And then there's a sequence that goes with mass, right? Low mass is on the right, high mass is on the left. And that also relates to the surface temperature. So low mass stars are cold, high mass stars are hot and luminous. Okay, but they all, if they're in the main sequence, share this feature that they burn hydrogen, right? Now, to fuse hydrogen into helium, that's like in the Big Bang, right? You have to bring 2 protons or 4 protons together, right? And these are charged particles that have the same charge, so they repel each other. The protons don't like to be close to one another because of electrical interactions, but there's a stronger force, the strong nuclear force that can overcome the electric repulsion. But for that to happen, they need to be very close enough because the nuclear force, the strong nuclear force, it doesn't have a long range, right? It's very strong, but it only acts very close. So you need to bring them close together, which means that the motion has to be fast enough to overcome the repulsion, which means that the temperature needs to be high. Okay, so the temperature in the sun is high enough to bring these protons together, and then they make helium, just like in the early universe, but under slightly different density conditions with less gamma rays that would destroy this nuclei. And then the energy that is released by this reaction, this is the important part, is again set by E equals mc squared, which is the difference between the mass of 4 protons and the mass of a helium nucleus. Okay, and the reaction is complicated, many paths. I don't want to bore you with the details. For a star like the sun, the temperature will be high enough at some point to burn helium into carbon through the so-called triple alpha reaction. And the sun's core is going to start accumulating an inert carbon core that unfortunately will never be, when it comes to making even heavier elements, will never going to ignite, right? The carbon will never ignite. And what we're going to be left with is a inert carbon core with some helium fusion and some hydrogen fusion. And that this will stop because electron degeneracy will take over and it will not allow the core to contract. And the outer layers of the sun are going to be expelled in a planetary nebula, like the one I showed you in the beginning. That's going to be mixed into the interstellar medium, and then we have a white dwarf at the center. And so we have a white dwarf at the center. You don't see it here. This is just gas that is ionized, and then the planetary nebula that returns the carbon primarily to the interstellar medium. Okay, so this is all this orange, right? Carbon and nitrogen, very abundant elements. Di-Loma stars plus a whole bunch of neutral capture elements that I'm not gonna get into. But the carbon and nitrogen, particularly carbon, organic molecules, think about that, right? Comes from planetary nebula. Then we have exploding white dwarfs. Most of you, I assume, have heard of type 1a supernova. Type 1a supernova are the same supernova that are used in cosmology to measure large distances in the universe, to measure things like the acceleration and the expansion and other aspects of it. And our understanding is that this should involve white dwarfs that are completely destroyed by a thermonuclear reaction, right? And the way you can make that happen is on the one hand, if the white dwarf is accreting from a binary companion that is usually a normal star, cross-binary interaction, the gravity is modified, tidal forces result in matter being pulled from the binary companion, and then the white dwarf gets hot, nuclear reactions begin, and the whole thing explodes. That's one possibility. The other one, this was a movie, we cannot watch it, but imagine these two white dwarfs spiraling into each other and then colliding and then exploding. So you have two binary systems, two white dwarfs in a binary system that merge and then ignite, and then you have an explosion. And that is a type 1a supernova. Yeah, the movie is not here too. You would see this point brightening with time, and this would be the light curve of the supernova. Brightness as a function of time, and then a spectrum that would show you the spectral lines as a function of time. And if you were to tabulate the brightness of a supernova as a function of time, you construct a light curve like the one we have here. So this is time in days, and this is luminosity and solar luminosity. So the white dwarf supernova, or the type 1a supernova, is this red curve that has a bump that arises from photons that are trapped in the blast wave that go out all of a sudden. And then you have this long exponential decay. Again, we have a log axis on the y-axis and a linear axis on x. So this is exponential. And the exponential decay matches the radioactive decay of nickel-56 and cobalt-66. So nickel-56 decays into cobalt-66, and cobalt-56 decays into iron-56, right, which is the stable form of iron, right? And this is how we know that most of the iron in the universe comes from type 1a supernova, because we can observe how many of them explode. We know how much mass is ejected per explosion. We do the accounting, and we find that they're the dominant contributor, or the majority contributor to the iron and iron group elements in the universe. And this is just a picture of Tycho's supernova remnant from the 1500s in the X-rays. That shows you the forward shock, and then narrow bands in the X-rays focus on some lines from elements that show you the elements are mixed up turbulently into the interstellar medium. Then we have dark blue exploding massive stars here. And massive stars, most of you know, explode as supernova. Different types of supernova than the type 1a or white dwarf supernova I showed you before. And this is possible because massive stars, by virtue of being hotter, they can support more advanced nuclear reactions that involve heavy nuclei. That's because they're very hot. And so these temperatures allow this nuclei to overcome the repulsion. Look at all these protons, right? Strong Coulomb force. And the interior of the star forms this onion shell-like structure with ever heavy elements toward the center. But fusion can only go up to iron, right? And beyond iron, fusion cannot produce any more energy. And the reason is that iron has what we call the smallest mass per nuclear particle, or technically we call it the binding energy. Nuclear binding energy per nucleon is the highest for iron. So iron is the most tightly bound nucleus, and you cannot extract any more energy by fusion. If you want to go to heavy elements, you need fission, like uranium, right, in nuclear reactors. But for fusion, like inside stars, you can only go to iron. And once iron accumulates in the core of the star, nothing can provide energy to support against gravity once it has grown above a certain size. And then the core collapses, and we have, again, a supernova explosion. This is a different light curve. Of course, this is the blue one. It's modified because instead of a white dwarf that blew up completely, we have a massive star that has an explosion coming from within, right? And so the blast wave sweeps up through the outer layers of the star, and so the light curve looks differently. Yeah. But again, there's some nickel produced, and so there's also some nickel-56 exponential curve, and then we have titanium-44 and other contributions. Okay. The last major puzzle in chemical element production in the universe were the so-called R-process elements. So these were, remember those little two peaks I showed you in the cosmic abundance curve at the end? Those involved neutron capture reactions that happen really quickly compared to the beta decay of this nuclei. So you form a stable nucleus and then they decay. But where in the universe did this happen was not clear, right? We knew the nuclear physics needed, the flux of neutrons that you need, and the expansion time, and the kind of paths in the nuclear chart that we needed. But where in the universe did these conditions were met was not clear, right? For a long time, neutron star mergers were thought to be a candidate, as were core collapse supernova. So this is just an illustration of the process. So you have a heavy seed nucleus like, I don't know, iron, and you capture neutrons. Now, why neutrons? Because neutrons do not feel the Coulomb repulsion, so they can just be captured really quickly. And what you're seeing here in the lower left is the nuclear chart. Okay, in the x-axis, sorry, we have the neutron number, and on the y-axis we have proton number, and these colors correspond to different isotopes. Okay, so let's say 20 would be, or 10, I think it's neon. Yeah, 10 is neon, and so each row corresponds to a different isotope, right? Because you have different numbers of neutrons. And these are the magic numbers, these black lines here, the magic numbers that I was telling you about, where the nuclei are very stable. And so nuclei in the R process moves through this red line in the diagram. And we didn't know where did this happen in the universe, and then we observed a binary neutron star merger in both gravitational waves and electromagnetic waves. This is the well-known GW17OS17 event. So the binary neutron star is such that the orbit decays by the emission of gravitational waves until they merge. We know of something like 20 systems like this in the galaxy. They're not going to merge anytime soon, but within the age of the universe. But LIGO was able to observe one of these, and our network of high-energy satellites that detect gamma rays also detected a gamma ray burst of short gamma ray burst, coincident with this neutron star merger. And subsequent observations in the electromagnetic spectrum showed that the properties of the explosion that accompanied this gravitational wave detection were consistent with a blast wave that is full of R process elements. And that is because the way matter interacts with the photons, we call that the opacity, is unique when you have a composition that is heavy in R process elements. There's many spectral lines that are not present, say, in iron, like opacities, like in type 1a supernova, right? So it's like a signature of that, and we saw it. And based on the brightness and the duration of the explosion, we can infer the amount of mass that was ejected. And of course, there's only one event, but LIGO has a certain sensitivity. And so if in a period of X many years you see one event, you can calculate how probable is that to happen. And if you know how much mass is ejected per event, you can calculate what is the enrichment rate. And that is roughly consistent with what we need to explain the R process abundance in the galaxy, right? So for now, we put a tick. So there's good preliminary evidence for R process coming from neutron star mergers, but of course there are open questions. And I think I went a bit fast, but that's okay because we were delayed. But I can just elaborate a little bit on the open questions. So right now, we don't know if neutron star mergers are the dominant or even exclusive source of R process elements. They can, by themselves, produce a substantial fraction of it. The problem is that we only have one observation that supports this production channel, and so we don't know if all of it comes from neutron star mergers or if there are other sites where this can happen. In particular, collapsers have been looked at as possible candidates. The reason is that when people study metal poor stars in the galaxy, okay, so you know that as I said before, when you have low mass stars and high mass stars, they return elements to the interstellar medium. You can think, okay, out of that enriched gas, I can form new generations of stars, and then those stars are going to again enrich the gas, and so on. And you have a cycle of stars being formed and then dying and returning the elements. And with the passage of time, you get a higher proportion of heavy elements. Right? So then you can look in the galaxy as to stars that have very low content of heavy elements, so which means that they're very old stars, right? And look at the R process abundance of those very old stars, and there's some controversial evidence that you need very quick enrichment in R process elements, right? And neutron star mergers take a while to produce the R process because the orbit has to decay by gravitational wave emission, and that can take easily 100 million years or more, right? Whereas collapsars and supernova operate on million-year timescales. And so the argument is, do we need an extra source that can operate really quickly compared to the age of the galaxy or not? That, if you go to conferences, that's the kind of thing you hear, okay? When it comes to the nuclear physics side, there's a couple of interesting questions. First of all, what are the heaviest elements that are possible, given the properties of the strong nuclear force and nuclei that can be bound? So I take you back to this nuclear chart, right? So the question is, how far to the right does this go? So the heaviest element produced in the lab is Z equals 118. It's called organezon. It was produced by a joint Russian and American team. And currently, there's a search for Z equals 120. It's difficult because these things are unstable, so they live for a short time, and you need to make them by sticking things together, and it's complicated. But this is one important area of research for heavy isotope facilities. The other one is the limits of nuclear stability. Right? In particular, if we go again to the nuclear chart, you see that this is neutron number, again, proton number. This is all populated. You see that here, there's nothing. There's a white portion of the diagram, and that means that we expect that nuclei cannot exist to the right of this band, because once you have too many neutrons, the nucleus is not stable, right? And the boundary of stability of this nuclei is called the drip line, right? On the neutron side, it's called the neutron drip line. On the proton side, it's called the proton drip line. And stable nuclei are those given by this. Is this the purple band, I believe? Yes, there are the stable nuclei, right? So all these are unstable, but measurements, laboratory measurements, are not done by any means in all this chart. It's only here, only for low mass nuclei, and the rest. You can imagine, if you want to produce an R process calculation, you need inputs, nuclear masses, beta decay rates, and so on. All of that is not known, it's just extrapolated theoretically, right? All of that, there's what we call nuclear mass formula to tell you the binding energy of heavy nuclei. We don't know that experimentally for most of that nuclear chart, right? And so facilities like Triumph in Vancouver, or FRIB in Michigan, or GSI, the GSI Helmholtz Accelerator in Darmstadt, Germany, are making measurements of neutron-rich nuclei to get at things like beta decay rates and masses that then we can use as inputs to these calculations. And of course, the real goals of those things are applications for technology or nuclear energy, right? But we benefit too because we can use them to make our predictions, right? But again, neutron-rich elements and the neutron drip line are active areas of research, okay? So just to wrap up, over the last 10 years, we have completed the inventory of cosmic element formation sites. So we know neutron star mergers now can produce our process elements. Then these are a major source of heavy neutron-rich elements. We don't know if it's the only one or the dominant one, but it's an important one. And then, of course, uncertainties remain about the limits of nuclear stability, the drip line, neutron-rich properties, as well as the most massive elements that are possible in the universe. And thank you. Have any questions?
Any questions for Rodrigo? Got one back here.
You very briefly mentioned at the beginning that in the earlier universe, the antimatter was created. Does that mean there is no more antimatter being created? And are there any new theories as to where all the antimatter that was created has gone?
Yeah, that's a good point. I didn't mention that. In the early universe, things were very hot and you have anti-particle creation, right? And we think that for the most part, there was almost equal numbers of particles and antiparticles, which is matter and antimatter. Yet now this world and us were made of matter, not antimatter. So that means that there should be an imbalance of matter against antimatter. And the rough order of magnitude for how much difference that was is basically the number of photons versus the number of baryons, like neutrons and protons, right? And the ratio is like 10 to the 9 more photons than neutrons. So that's really the rough estimate between the imbalance between matter and antimatter. And right now, as far as I know, that's an open question in physics. Why there's an asymmetry, or like the breaking of symmetry between matter and antimatter. And there are things like double beta decay experiments that are looking for whether the neutrino is a Majorana or what was the other particle? Dirac, thank you, Sharon. Dirac particle, and that has clues as to whether you have known ways in which you can go beyond the standard model and break the symmetry. But as far as I know, that's a very open question in particle physics, high energy physics.
Any other questions? Got one back here.
Hey, thank you for your talk. So the neutron star collisions, is there any sort of conceptual accounting on if a predecessor collision where we are now would have created the amount of heavy elements on Earth greater than zinc? So that would be the copper, the gold, the vanadium, etc.
Yeah, thank you. That's a good question too. So there's various lines of research to answer that question. So was there a neutron star merger close to the solar neighborhood or not, right? And so that involves first whether we find evidence, say, in nearby stars that are, say, over-enriched over others. So if neutron star mergers are the dominant source, then one would expect that the abundance is not homogeneous, right? Because these things don't happen all the time. They happen one here, one there, like the rate is very low compared to supernova, right? But then there's the issue of mixing, because the interstellar medium is turbulent, so the gas in the galaxy is overturning. And so people do calculations like having a galaxy simulation and then inject neutron star mergers here and there and see if you can, like when you mix smoke in the air, right? The turbulence mixes it, whether the mixing rate is fast enough so that you homogenize compared to the time scale at which you're forming the stars. That question is still open, right? But the unknowns are the ones that I was just trying to outline. I don't know if that answered your question.
Thank you.
Yeah.
Two more questions.
Thank you. You would expect transuranic elements to be generated during some of these processes. Are there any suggestions of how you might possibly observe that?
Good question. So what we do see is that most of these things are very unstable to spontaneous fission or induced fission. If we have data in the lab of spectral lines, that would be if they're in stable form, right?
Right.
You can look at the stars in the galaxy and see if they show those lines. If they're unstable, it depends on the half-life, but if they're like, milliseconds, seconds, even years half-life, there's no easy way to get those lines observed in a transient, right? For example, this kilonova, which is the little transient associated with neutron star merger, expands at something like 30,000 kilometers per second, right? And so the lines that for stars, right? Stars are just sitting there orbiting, but they're not doing much. They're very narrow. For these things, the Doppler effect broadens them, and you get blending of the spectral lines. And it's just almost like a whole continuum. It's really difficult to say, oh, we had this specific heavy element, and if we don't know, don't even know them in the lab, right? It's even harder. Right? So
Thanks.
I happened across a book that explained some years ago that all the heavy elements on Earth were caused by a succession of supernova. One seeded a gas cloud with a certain amount of material. That gas cloud coalesced and formed a second star that went supernova. But that apparently is now discounted. What can you tell me what caused that theory to be discounted?
I'm not familiar with that specific theory. Typically, when people try to reconstruct the local history, they look at things like ocean floor sediments or like tree, like rings and things like that. And to my knowledge, there's no major at least in the recent 10 years or so, that has been a major shift in whether people think or not that a supernova was happening nearby. There's some groups that specialize in that, and then they kind of argue with each other. But I don't think it is a broad consensus in the community, at least the nuclear astrophysics community, that yes, there was a supernova, then no, there wasn't. I think it's very much an open question.
Last question.
Thank you for the talk. When you have two neutron stars colliding and you have neutrons going everywhere, hitting heavier elements, are you having fission reactions happening at the same time as you're having the rapid absorption of neutrons and the formation of these heavier elements? And if so, what makes the growing of the heavier elements overpower the fission that's happening?
Yeah, that's a good question. So the can get a bit technical, but it all depends on what's the proportion of neutrons and protons that you have. And you might say, oh, but the neutron star is all neutrons. Well, what happens is that when they collide, they heat up to the point that everything becomes a soup of neutrons and protons, right? All the binding, it just dissolves, right? So we say it reaches nuclear statistical equilibrium, right? And then you might say, okay, it's like 97% neutrons and 2% protons as a neutron star. But then the thing is that things are hot enough that neutrinos are emitted, right? And neutrinos can change a neutron into a proton or a proton into a neutron. And then the question becomes, what is the ratio of electron neutrino fluxes versus anti-neutrinos of electron type? And those can change the composition and then can raise the ratio of protons to something like 20%, 30%, right? And that ratio then, once the matter expands, it cools, right? Tells you how many free neutrons you have to capture, right? So if you have a lot of free neutrons, what happens is that as you were anticipating, you build up a very heavy nucleus, say uranium, right? And then it spontaneous to fission, right? But those fragments, the fission fragments, start capturing neutrons themselves. And then they fission again, and you have what is called a fission cycle. And that fission cycle turns out that results in an abundance pattern. If you look at that, so we have mass number and abundance here on the y-axis, from 160 to 200, second to third hour process peak. That abundance pattern observed in the sun, in stars, and so on is really robust. It doesn't really matter where you look at it, it's really robust. For lighter element, it varies a lot, but for that, it's really robust. And theoretically, it comes about because of fission cycling, right? So fission is thought to play a super important role in establishing that near universal abundance pattern for at least the heavy portion of the R process elements. So yes, fission is is pretty important. But it's this cycling of fission and capturing.
Thank you, Rodrigo. Can we have a round of applause for his presentation? On behalf of the Royal Astronomical Society, a little token of our appreciation.
Thank you.
You're welcome. Okay. Okay, next we're going to have Murray Hunt, who going to give a quick talk from the observers group. Murray?
Well, hi. Hello, everybody. It's Alistair and I, and with help from Berta Beltran, will be leading the observers group for now. My name is Murray Hunt. I haven't actually. About 20 years ago, Jeff Robertson said to me, "Hey, there's astronomy meeting. I'd like to come, and I'd like to come with me." So I said, "Sure, I like astronomy," and so I came, and Jeff Robinson was so excited, and I fell asleep. So I flashed forward about 20 years, and I retired, and I still like astronomy. So I joined. Jeff was president at the time, and I still, as I say, I still fall asleep sometimes, but not at my telescope. So we are trying to a team approach, and we've had a Zoom meeting about 3 weeks ago, our first Zoom meeting of the newer group. And we had great attendance. We had sort of a round robin discussion, introduction of people, and we found people who were observing with their eyes, with binoculars, with their telescopes, and a great little discussion about eyepieces. But since then, we've had two different times where the skies were pretty clear, and we met just informally. And we had about 9, 10 people the first time. And we saw Mercury, Saturn, Venus, Orion, before his clouds rolled in. I still remember one of the fellows called out. He was actually looking through a telescope when Mercury set. And I thought that was pretty darn neat. Yeah, that was really neat. That's neat. And then I went away on holidays. So Alistair met with another group, and well, maybe some more about that. But our hope is to continue this. Clear nights in the city, if 1 or 2 or 3 of us are available or more, then we'll get together somewhere, Facebook or the Astro List will announce it, and anybody is welcome to come. And we'll have telescopes, binoculars there, and yeah. When I first started, I started going to the observers meetings, and Larry Wood was one of my main first mentors, Denis Boucher, Alistair Ling, and learned a lot. And I find myself, I'm more of a stargazer. I'm not really, anyway, I really enjoy stargazing, and I think that's one of the best terms for it. So next Wednesday, first of all, Thursday night, Friday is a lunar eclipse, total eclipse of the moon. And I guess the weather isn't looking good for it. But if so, I think the deck may be open here. But anywhere in your backyard, if you can see with your eyes or binoculars, or telescope, that'll happen between something like 11:30 and 3 o'clock in the morning. You need a good southeast view, about 30 degrees up or so, 30 to 35 degrees, and you'll see the moon and go into eclipse. Total eclipse being about an hour. And then March 19th, we'll have the next Zoom meeting. It's the week after the general meeting. We're trying to standardize on that. And what else do I want to say? We're going to try to, there's been some interest in learning about some of the basic, for me, it was mentoring and just observing with other people. And then the astronomy, the RASC observing programs really helped. And they gave me direction to my learning. I kind of came in kind of late in years. So I directed my learning with these programs. I've done several now, and I found them really, really helpful. So we're going to have a little discussion about usually the first one, explore the universe. Something you can do with naked eye and binoculars. And for the most part within the city, although dark skies are always the best way to go if you can. And what is an observation? Perhaps introducing a logbook, perhaps description and sketches. And and then we'll just open to wide discussion. So that's March 19th. Alistair, anything?
Yeah, thank you, Mary. I'll just leave us here with where's my page down? There it is. Okay, yeah, here's a picture of what it was like a couple of weeks ago. Just a handful of people gathered around scopes. Venus is the one shining through the clouds. We had Mercury just a little bit earlier. And so we've got the time to show people this and that, sometimes Jupiter or a star cluster. And if you've got a problem with your telescope, there's somebody said, I've got this, I can't make this work. And it's just like, oh, try this, try that, and boom, we get you working. And sometimes it's try a different eyepiece. This eyepiece, I just can't seem to get it to, try this one. And is it the telescope or is it the eyepiece? And all of a sudden it's sort of super easy to resolve any problem when you're in a group of people and you've got some experience there to help out. So the exercise for you for the next month is to simply look at the sky. As our dear Lucian Campbell used to say, you can observe a lot just by watching. And so stand outside in the sky for a minute. Doesn't matter. I mean, it's not going to get too cold anymore. It'll get chilly a little bit if you're out in shorts and a t-shirt, but these days, look up into the bright winter triangle. There's Orion down at the half of it, down at the bottom there. But Jupiter in the lower right is slowly moving to the left relative to the stars. So you use Aldebaran at the bottom, Capella at the very top, and you can see they don't quite make a straight line anymore. Jupiter passed that straight line just a little bit while ago, but Jupiter will then cross and make a straight line with LNAP. And so you'll be able to watch that the red markers there is the motion from this meeting to next meeting. So by the time we hit next meeting, Jupiter will be at the end of that red line. And so you will be able to see, oh yeah, it's making a straight line. Oh, now it's passed. And the same sort of thing for Mars up at the top there, Castor and Pollux. One of the little mnemonics is which is which? Well, Castor is closer to Capella and Procyon is closer to, or Pollux is closer to Procyon. So the C's go together and the P's go together. That's how we remember. But at any rate, watch how Mars changes its shape from, it's almost going to be a perfect right angle triangle at Pollux, and then it'll make a straight line with, I think that's Eta Gem at the bottom of Gemini there. And then it'll pass that straight line. And then it'll become a straight line in a month's time with Castor, Pollux, Mars. So just to go out, have a look and watch. And it only takes a few minutes, and every sort of 3 or 4 days, you should be able to go, oh yeah, it's moved a bit. So that's all it takes to observe. So come on out. If it's looking fairly cloudy, but hey, we often get sucker holes or miracle holes. And so we might get lucky Thursday night. The eclipse is technically on the 14th, but because it's an overnight event, it's actually the Thursday night, the 13th. And then in quite a few more weeks, May the 3rd, International Astronomy Day, come on out. We'll have telescopes looking at the sun, and later on in the afternoon, the first quarter moon will be something like that. Will be up in the sky. So come on out, support us, and have a look at the sky. Okay, thank you.
Thank you, gentlemen. Now, just to make sure that the lunar eclipse so far, the long-range forecast for Thursday night, Friday morning is not looking very good. So I'll have to have, who here has bought a telescope in the last 30 days? Okay, you guys are all safe. We'll find that person. Just seems every time there's some type of astronomical event going on in Edmonton, the old 80-20 rule, 80% of the time we're going to get weathered out. 20% of the time we'll get lucky. So it looks like we're on the 80% curve this time. We're going to get Murray up here. He has a few things he wants to share with us tonight. And then after that, we'll have a quick trivia question for you and the break.
This isn't going to take too long here. This spring, we've been listening to radio broadcasters and people all over the place talking about this lineup of planets. And now I have to figure out how I go to the next slide. The right arrow? That's as right arrowing as I can go here. There.
Good enough.
Mouse. So anyway, this is a shot of the what the layout of the planets looked like in June or in January, and the lineup of the planets. Well, Uranus, Jupiter, Mars, Earth, and Venus in the evening sky. And do I have a laser pointer up here? No, I do not. Okay, we'll live without it. But they made a sort of a nice line in the evening sky. Ah, there it is. And you can see it running there. But I don't think it was a really great lineup. So if we go to move forward to March 21st, which is in just a week and a bit's time, actually, we get a really wonderful lineup of the planets, and I will point that out here. There's Earth, Venus, Mercury, Saturn, and Neptune. And the joy and the wonder of this is that, I'll zoom in, and you've got this lovely lineup of the planets. But the bad thing about this lovely lineup of the planets is that they're all around the sun. So none of this is really visible, even though this is the official lineup of the planets. But one thing is really quite fun, and that is that Venus will be passing about 7.5 degrees above the sun. And this is actually something that's really wonderful. I hope people can get out and find a safe place where they can get in the shade of a building or something like that, so that you can't see the sun, but if you peek above where the sun is, you'll be able to see the planet Venus about 7.5 degrees above the sun. And when you do that, you'll see a razor-thin crescent. It's absolutely beautiful. The first time I saw this was when I was a kid, probably about 13 or 14 years old, pointing a telescope too close to the sun to be safe, but I saw a narrow crescent Venus, and I've always found it's absolutely beautiful. I don't know if the observing deck would be open on the Saturday, but the Saturday is the day of closest approach, and if the observatory isn't open, well, if you can get out and find a safe place to look, the important thing is don't let the sun get in your eyes. Blind astronomers are virtually non-existent. So that is my 2 minutes on the stage. So thank you very much.
Okay, so what we're going to do is go to a quick trivia question here. Okay, 3 questions. Okay. So this should be somewhat simple to some degree. What is the name of the largest volcano in the solar system and what planet is located? which planet in our solar system has the most moons and how many does it have? And which planet in our solar system has a day longer than its year? And what are those lengths of a day and year? So we'll get to that after the break. And let's try to keep it short, 10 minutes max. We've got a few more things we want to get to before the end of the night. So if you have any, if you got some time, grab some refreshment, and we'll be back here at 9:05.
Let's all go to the lobby. Let's all go to the lobby. Let's all.
Okay, everyone, if we can get back to our seats. Please get back to our seats. Okay, we have a few, maybe with a couple announcements here. So I keep bringing this astroperic members perk, bring it up again every month. It's a great cloud and smoke forecast tool. I was looking at it today, and that's why I'm thinking the 13th and 14th aren't going to be all that great. So if you're interested in getting that app on your computer or your smart device, then a request to join the RASC Edmonton Center group. Okay, last month I was involved in a national town hall meeting on citizen science, and talked to a couple people about that since then, and decided that we're going to create a citizen science committee, and Jay Lavender has volunteered to chair that group. So basically, these were some of the projects that came out of the meeting at the end of February with respect to some of the centers who were doing citizen science. So all sky cameras, Hubble archive projects, Zooniverse, large data star surveys, exoplanet photometry, spectra of variable stars. That seems to be a popular one right now, but it could cost a little bit of money to get into it. But as you can see, there's quite a few projects that have been brought forward at the national level that some of the citizen science project that we could look at. So I think over the next month or two, under Jay's guidance, we'll take a look at, see if we can come up with a couple, maybe 3 projects. Don't have to necessarily be on this list, but we're hoping to be able to see if we can get some traction on doing some citizen science here at the center. Montreal, Halifax, Winnipeg, Calgary, they all seem to have a group that are doing some form of citizen science at this time. So hopefully we can get some more information out to you through the website and at the next meeting in April to talk more about what we're looking at. If anybody has any ideas that they want to try, that particularly not on this list, just send me an email at president@edmontonrasc.com, and I'll pass that on to Jay, and we will start working on something. Okay, we're going to go to Book of the Month Club, and I'm going to invite Mark up to talk about it.
Thank you. Good evening. Hello from Rosemary Ball and I are co-librarians at the Kemble Library, which is located just off the main entrance of the Star Theatre here. The library is open about half hour before the meeting and 15-20 minutes after the meeting. And we have books to lend out to members. And actually tonight, if you look at the ledge over there, we have some surplus books that are free. So have a look at those books over there. Book of the month, this month, the book of the month is Alpha Centauri by Martin Beach, who's a professor at the University of Regina. course, Alpha Centauri is our closest stellar neighbor at 4.4 light years away. It's also one of the brightest stars in the sky. And as far as the rankings of bright stars go, how does it rank? Is it first, second, third? I believe it's third, behind Sirius and Canopus. And it's easy to find. You go 80 degrees straight south of the star Arcturus, and you can find it. Arcturus is the fourth brightest star in the sky too. But there's a problem there. If you go 80 degrees south of Arcturus, you're ending up way in the southern sky, and hence you can't even see Alpha Centauri. From here, you have to go to, in North America, you have to go to Florida, just to have it poke above the horizon. So that's what happens when you have a star that's has a declination of minus 60 degrees. Actually, in both the polar regions of the sky, there aren't many really bright stars. For example, in the northern sky, how many stars brighter than second magnitude are there? Let's say poleward of plus 60 degrees. Any guesses? According to the Observer's Handbook, looking at the table of bright stars, actually Polaris itself is sitting right around second magnitude. There's only one that's brighter than that, and that's one of the stars in the Big Dipper, Dubhe. It's a little better in the southern hemisphere. You've got Alpha Centauri, which is sitting at minus 60 degrees. Then you got A Crux in the constellation of Crux, which is at minus 63. And the furthest really bright star is Mia Placidus in Carina, which is sitting at minus 69 degrees. Clayton informed me that Mia Placidus is also one of the neighbors of his, a few years down. Mia Placidus gives out the most Halloween candy every Halloween. Anyways, let's find out a little more about this book. As our closest stellar knit companion and composed of two sun-like stars and a third small dwarf star, Alpha Centauri is an ideal testing ground of astrophysical models and has played a central role in the history and development of modern astronomy, from the first guesses at stellar distances to understanding how our own star, the Sun, might have evolved. It is also the host of the nearest known exoplanet, an ultra-hot, Earth-like planet recently discovered. Just 4.4 light years away, Alpha Centauri is also the most obvious target for humanity's first directed interstellar space probe. Such a mission could reveal the small-scale structure of a new planetary system and also represent the first step in what must surely be humanity's greatest future adventure, exploration of the Milky Way galaxy itself. For all of its closeness, Alpha Centauri continues to tantalize astronomers with many unresolved mysteries, such as how did it form, how many planets does it contain, and where are they, and how might we view its extensive panorama directly. In this book, we move from the study of individual stars to the study of our solar system and our nearby galactic neighborhood. On the way, we will review the rapidly developing fields of exoplanet formation and detection. So the book is available after the meeting. So thank you very much.
Thanks, Mike. Okay, we have next up is Astro Imaging Corner with Tom Owen.
I'd like to welcome everybody to Astro Imaging Corner number 144. It's been going on for 144 straight months. And let's just get right to it. So I like to start off by just having some commonly used terms that you're going to hear possibly tonight. Subs are individual short exposures. Stacking is the process of combining them to increase detail and reduce noise. And noise is the visual equivalent of the static you'll hear when you're listening in your car radio to a Blue Jays game in Calgary. And the visual aspect just gives a really grainy look to pics, and it's something that we all try to deal with. And the initials LRGB, HA, O2, and S3, those are abbreviations of the names of filters that are used in mono cameras. HA, O2, and S3 being narrowband, hydrogen alpha, oxygen 2, and sulfur 3. Messier, you'll hear, Messier 79 or Messier 106. It's a catalog of what is now 110 deep sky objects. It was first compiled and published in 1774 by the French astronomer Charles Messier. And as he was doing them to tell you what not to look for, he was a comet hunter. Finally, Bortle scale, that's the measure of the brightness of the sky at night, with 1 being darkest and 9 being brightest. And downtown Edmonton, it goes all the way up to 11. Okay, so let's carry on. So our first image is from Brian Martin. It is the Orion star forming complex. And he says, attached is a nightscape of the Orion star forming complex above a now desanctified Ukrainian Catholic church in the Coppernick community south of Bruce, Alberta, about 30 kilometers southeast as the crow flies from BNLO. A good Bortle 3 sky, which helped bring out Barnard's Loop, the Rosette, the Lambda Orionis ring, and even the Witchhead Nebula to the right of Rigel. The image of the sky was taken on a modified Canon 6D with a Tamron 35mm SP at ISO 800, f1.8, and the sum of 21, and it's the sum of 21 2-minute subs. The foreground was a pano of 2 4-minute exposures with the Canon 6D and a 50mm Sigma art lens at f5.6. The image was taken the evening of February 25th. Some thin cloud helped to bloat the brighter star images, which also helps to accentuate color. And I think this is a great image. It is Warren Finley-esque. I just think that these kinds of photographs, I find them very, there's a lot of emotion in them, and I really, really enjoy them. So this is from Brian Alford, and as you can see, it's the constellation Orion. He says that it was taken February 27th, and the location was Black Nugget Lake. He used a Nikon Z780 camera, a lens at 50mm prime, ISO of 1250, aperture of f1.8, and an exposure of 10 seconds, and that's a really great image. So this image is from Ray Wiens, the Horsehead Nebula, and M42. So we're kind of zooming in on Orion through these images. This was taken with a QHY 367 attached to an ASCAR 300mm mounted on a ZWO AM5N, and it consists of 5 hours of data, 290-second subs, stacked in APP, which is Astropixel Processor, and processed in Lightroom, and it was taken from 33 degrees latitude, and I think this is just an outstanding image. So this is, of course, the Horsehead and Flame Nebula. Again, we're sort of zooming in. I took this, and this is in the constellation Orion. Of course, the blue star is Alnitak. It's the lowest of the 3 stars that make up Orion's belt. And these nebulae, they're touchstone objects for me. I like imaging them every 3 or so years just to see how I'm progressing, or at least not yet declining. This was taken in Bucerias, Mexico, which is a little town north of Puerto Vallarta, the last week in February. And Orion is nice and high in Bucerias. Bucerias is at latitude 20 degrees. So the auto-guiding was accurate and smooth. Any of you do any sailing, it's kind of, when it's nice and smooth, it's like sailing on a reach, and the air was nice and still. So this image represents a total of 3 hours, 10 minutes, using 5-minute subs in HA, O3, and S2, with the QSI 683 camera, a 90mm triplet, and a 1.6 focal extender. And the subs were processed using Astropixel Processor, were stacked using Astropixel Processor, and processed using Star Tools. So this is from Daniel Tomsey, the Monoceros Loop. He says that it's a section of the constellation Monoceros. The rest between Canis Major, Canis Minor, and Orion. Over 26 hours of subs were stacked to generate this image. The data was taken over 9 nights, December 28th, and then January 6th, 8th, 13th, 24th, and 26th, February 15th, 16th, and 17th. The Rosette Nebula, the Cone Nebula, and the Christmas Tree Cluster are clearly visible together with Hubble's Variable Nebula, which is NGC 2261. And this is taken from the Bortle 9 Edmonton University campus. And we were having a little chat about this at the break. And he's amazed that his narrowband images, his narrowband subs actually eliminate the lights of a helicopter as they're constantly going to and from the university hospital. So that's pretty amazing. So the capture details are the mount was a ZWO AM5. He was using a Minicat 51 and an ASI 2600mm Pro. The filters were SHO and LRGB. The guide scope and camera was a Williams Optics 32mm f4 guide scope with a ASI 120mm mini, sorry. The image processing software he used was PixInsight, so a great image. So from Hans, we have the Rosette Nebula. And again, we're kind of zooming in on things. He says he's got images of 2 nebula that are similar in kind and appearance. Both are emission nebula with H alpha regions. However, they're quite different in age and size. So you have the Rosette Nebula here, of course, and it is 5,000 light years distant and has a diameter of 130 light years. The other one, the Tribble Nebula, with its open cluster, which is NGC 1624, is 4 times further away, but only 4 million years old, and it's got a diameter of 20 light years. So it's less than a sixth the diameter of the Rosette. So the Rosette appears brighter and 25 times larger in the sky than the Tribble. He said, we find the Rosette is in Monoceros and the Tribble in Perseus, but I found it interesting to show the size difference by superimposing the small Tribble in the image of the Rosette at top right. So there it is right there. The second file is the actual image of the Tribble Nebula. And there it is. Both images were acquired in January and February from my Bortle 7-8 backyard. The Rosette at 528mm focal length for 6 hours in HAS203, and the Tribble Nebula at 1650mm focal length for 8 hours, and he used HAN03. So outstanding images, Hans. Now for something completely different. This is a moonshot from March 5th in downtown Edmonton using a 585 MC camera, a UV IR cut filter, and a Celestron CPC 800. These were 800 frames stacked using ASI Studio and processed using Star Tools. And the ASI 585 MC, it's a popular camera. It's capable of deep sky. It's relatively cheap, but it has a reputation as being a great lunar camera, and I really think that reputation is borne out in this photograph. The next few images are from yours truly. We didn't get any other images from other astro imagers, so I'm just going to show you what I was able to do when I was in Bucerius. So this is the Northern Jewel Box. It's NGC 2367. It's in Canis Major. It's about 4,900 light years distant and 10 light years across. And if you see right in the middle, this misshapen sort of thing, well, it's not really a misshapen. It's the supergiant Tau Canis Majoris, which is itself a 5-star system. So it's sort of the one star that binds all the others. It's a young cluster, relatively speaking, so all the stars are blue. It was taken with LRGB filters in the QSI 683, again with a 1.6x focal extender, using 3 and 2 minute subs for a total exposure of 41 minutes. Here's another cluster I took from Bucerius This is NGC 2477. It's an open cluster in the constellation Puppis. And at magnitude 5.8, it would be visible to the naked eye under very dark skies, appearing as large as the full moon. It has various nicknames which aren't very good, so I'm not going to repeat them. It contains about 300 stars, and it's about 700 million years old. The bright, large blue star is Beta Puppis, and it's not part of the cluster. And this is 15 1-minute subs in LRGB using the same equipment. And finally, this is NGC 2736, aka the Pencil Nebula. It's a supernova remnant in the constellation Vela. It's about 815 light years distant. Now, for this object, I used the HA and O3 filters, 4-minute subs mostly, for a total exposure of 5 hours and 14 minutes. I used the 1.6 extender, but I binned the subs because it's a very faint object. And it was difficult because it's only about, even down in Bucerius, which is at 20 degrees latitude, as I mentioned, it's less than 20 degrees above the horizon. So your counterweights are parallel to your telescope when you're trying to auto-guide on this thing. And the auto-guider protested a lot. Let's put it that way. However, I would like to go back and take more subs, but there it is. Something we don't see every day. Subs were stacked using AstroPixel processor and processed using star tools. I would really enjoy seeing more images from all of you and from everybody out in Zoom land. You don't have to be a champion astrophotographer. I'd really like to see what you're doing. We'd all like to see what you're doing and how you're starting out. And every step along the way is an accomplishment. So why don't you share your accomplishments with us? We all would really appreciate it. And that's all. Thank you very much.
So trivia questions were: name of the largest volcano in our solar system, which planet has the most moons, and which planet has a day longer than its year. Olympus Mons on Mars. Largest known volcano standing at 22 kilometers high. Which planet in our solar system has the most moons? Saturn with 82 confirmed. As of the current data, Saturn has 82, surpassing Jupiter's 79. And which planet solar system has a longer day than its year? Venus' day is 243 Earth days, and its year is about 225 days. So it's very slow rotation. Anybody get all of those? Okay, Tom. Did you look it up? Okay. Final announcement. So you saw the observers group. They were doing their thing again tonight. And if you're really interested in learning more about visual observing, get in on their webcast, on their Zoomcast, and go from there. Next monthly meeting will be on Monday, April 14th, and that will be a members' night. So any member who would like to make a presentation, please send that information on to me at president@edmontonrasc.com. And our cartoon of the month was submitted by Bob Lawrence. I only got 2, so we need a few more of those coming in. Okay, so here it is. I figured it was appropriate since we have a full eclipse coming on this week, which I would like to reiterate that is obviously weather dependent, and weather's not looking good at the moment. I understand if the weather is good, the RASC Observatory will be open. Jeff, what time approximately would it be open, weather permitting? 10 o'clock?
11-ish?
11-ish?
Yeah.
Okay,
That's just before,
because it starts about 11:09.
7:09.
Yeah.
Maybe 10:30.
10:30, okay.
Well, I'll
If
hear
the
myself
weather's
at
holding
10
and
o'clock,
you
so-
can actually see something in the sky other than cloud and snow. The deck will be open at 10:30. Anybody who wants to bring their own scopes out, welcome to do so. You can set up on the lawn in front of the observatory.
Probably not with the snow out there if we have snow. So probably along the walkways are the
Okay.
best places to set up.
Okay, so yeah, there probably will be snow during the week, so yeah, the walkway might be better. And other than that, if anybody have any questions, Murray does.
I'm sorry, I should have blathered this a little bit earlier, but St. Albert has their astronomy day on April 4th. It's just that we'd like to be able to get little kids that can come out and see something in the telescopes. So if anybody would like to join us in St. Albert on Friday night, Saturday night, the 4th, 5th of April, you're being most welcome with our group. So anyway, you can contact me at either new members on the link on the website or murray.paulson@gmail.com. Anyway, thank you.
One last thing I forgot to mention at the end is that I don't know if anybody heard that the All-Star telescopes was broken into early this morning, and a number of these binoculars were stolen. And they figured that they may be up for sale online in the not too distant future. So if anyone happens to be online on any of the Kijiji Marketplace or any other website that's offering equipment, and you see some brand new Zeiss binoculars at a very reasonable price, might give All-Star a call and let them know. Thanks, Murray. And I was mentioned earlier that Astronomy Day will be held on May 3rd, I believe, here at the Telus World of Science. So we'll be involved in that. And of course, again, weather permitting, the deck will be open. Okay, since that's it, and we're running a little late, 9:42, I will adjourn the meeting. Thank you for attending.